In this video, we're going to talk about eigenvalues and eigenvectors of a linear transformation T. Well, if we have that T of V equals lambda V for some real value lambda and some non-zero vector V, then we say that lambda is an eigenvalue of T and this V is an eigenvector of T corresponding to the eigenvalue lambda. So this definition is very similar to the definition of eigenvalues and eigenvectors of a square matrix. Now, because T of V equals to AV, where A is the standard matrix representation of T, eigenvalues and eigenvectors of T are eigenvalues and eigenvectors of the standard matrix representation of T. So let's try to find the eigenvalues and eigenvectors of this linear transformation. This is a linear transformation from R3 to R3. So to find these eigenvalues and eigenvectors, we need to find the standard matrix representation of T. So we need to find T of E1, that is the image of 1, 0, 0. So x1 is 1 and x2 and x3 are 0. So that image is 1, 2, 1. We also need to find T of E2. So that is the image under T of the vector 0, 1, 0. This vector has x2 equal 1 and x1 and x3 equal to 0. So that image is 1, 0, negative 1. And we also need T of E3. So that is the image under T of the vector 0, 0, 1. So x3 is 1 and x1 and x2 are 0. So we have minus 3, 6, and 5. So the standard matrix representation of T is the matrix A, which has as columns T of E1, T of E2, and T of E3 in this order. So that is the matrix 1, 2, 1, 1, 0, negative 1, and negative 3, 6, 5. So we need the eigenvalues and eigenvectors of this matrix. So let's find first A minus lambda I. A minus lambda I is the matrix that I get by subtracting lambda along the main diagonal of A. So that is 1 minus lambda, 1, negative 3, 2, minus lambda, 6, 1, negative 1, and 5 minus lambda. Now we need to find the characteristic polynomial of A minus lambda I. That is the determinant of A minus lambda I. So I will expand along the first row. So that is 1 minus lambda times the determinant of this 2 by 2 matrix minus lambda minus 1, 6, 5 minus lambda minus 1 times the determinant of the matrix 2, 1, 6, 5 minus lambda plus negative 3 times the determinant of the matrix 2, 1, minus lambda minus 1. So let's figure this out. This is 1 minus lambda times, well, this product, so that is lambda squared minus 5 lambda minus this product. Well, this product is negative 6, so minus negative 6 is plus 6. Minus 1 times this, the determinant of this matrix, so this product is negative 2 lambda plus 10 minus 6, this product is 6, minus 3 times this product, which is negative 2, minus this product is negative lambda, so minus negative lambda is plus lambda. So let's simplify this a little bit. This is 1 minus lambda. I can factor this to lambda minus 2 times lambda minus 3, and this here is equal to negative 4 minus 2 lambda, so negative 4 minus 2 lambda, positive 4 minus 2 lambda. So when I multiply this by negative 1, I get plus 2 lambda minus 4. And over here, I would have, let's multiply by negative 3, so lambda minus 2. So I see that lambda minus 2 is a factor in all of these terms. So I'm going to factor this out. And from the first term, I have 1 minus lambda times lambda minus 3. From the second term, I have 2 left over, and from the last term, I have negative 3. So this is lambda minus 2. Let's multiply this out. I have negative lambda squared minus lambda times negative 3, so that's plus 3 lambda plus 1 lambda, so that's plus 4 lambda minus 3 minus 1. So that is lambda minus 2 times negative lambda squared plus 4 lambda minus 4. Let's factor negative 1 out of there. So I have lambda squared minus 4 lambda plus 4, and that of course is lambda minus 2 squared. So I end up with negative lambda minus 2 cubed. So there's only one eigenvalue. T has only one eigenvalue, and that is lambda 1 equal to. Now we need to find the eigenvectors of T, or eigenspaces of T, which are the eigenvectors and eigenspaces of A. So we need to find the null space of A minus 2I. Well, A is the matrix 1, 2, 1, 1, 0, negative 1, negative 3, 6, 5. So from this, we're going to subtract 2I. So the matrix A minus 2I is the matrix negative 1, 1 minus 3, 2 minus 2, 6, 1 minus 1, 3. And it's very easy to see that this is row equivalent to the matrix 1, negative 1, 3. It's because this row is a scalar multiple of this row, and this is just the negative of that. So all three rows are scalar multiples of 1, negative 1, 3. Now let's call this vector here, this matrix here, H. So we need to find all the vectors x such that hx is equal to 0, and of course x is of the form x1, x2, x3. Well, there is no pivots in these two columns here, so we're going to have two parameters. We will have that x1 minus x2 plus 3x3 equals 0. That means that x1 is equal to x2 minus 3x3. So the vector x is of the form x2 minus 3x3, x2, and x3. So this is x2 times the vector 1, 1, 0 plus x3 times the vector negative 3, 0, 1. So the eigenspace E lambda 1 of A or of T is the span of the vectors 1, 1, 0 and the vector negative 3, 0, 1. So we can now say that this here is the eigenspace of lambda 1 equal to of T, and any non-zero vector inside E lambda 1 is an eigenvector of T. So we could say that any V which is not equal to the zero vector, but V belongs to E lambda 1 is an eigenvector of T corresponding to eigenvalue lambda 1 equal to.